All right, kids, we are moving along in Unit 9. This is Section 9.8. We've got one more after this in our BC Calc Adventures. So Section 9.8 is called Area Bounded by a Polar Curve. In geometry, we learned that the area of a sector of a circle is 1/2. You might or might not remember this. The theta, the angle, times r squared. And that's going to come up a lot because look at this is like a sector of a circle, like a piece of pizza, where this is a sector of a polar function. Sometimes the curve is smooth and pretty like this, but sometimes it might have a little something else going on that kind of dips in or out of the sector. So we're going to relate the two. The radius of a sector for us, the radius would be, see how it's changing? Like this could be a radius going from that point to this. This could be a radius as well. So it's f of theta, whatever theta is. That's what your R, oh my goodness, that's what your R is going to be. There goes Levi. All right, the central angle. If I want to know what the central angle is, that's the angle over here. We're going to call that theta. It's like a change in theta. And the change in theta, also they use beta and alpha. Kind of the same idea as B and A. So this is going to be beta. Why does it happen that as soon as I turn the record on, their dog goes crazy out with something outside? Over n. We'll talk more about that in a minute. But let's go back to our sector of a circle up here, just in a regular old geometry kind of way. This central angle is theta. This is your radius going from the center to the edge of the circle. And usually your theta angle goes this way. Same thing's going to happen with our polars. So I look at this, and this is usually from, you've got some situation, this would be like your A value and your B value, but they don't really come up with geometry stuff. So I made them really teeny tiny, but same idea as what we're talking about with the polars. So our area is going to be, and I'm going to bring in some fancy pants math talk here, and then I'll make it simple in a minute. The sum of t equals 1 to n, and I'll explain what this means in a minute, of 1/2 the change in theta times f of theta squared, and that's what you're looking at. So what on earth is that? And here's what it's saying. This is 1/2, just like this is 1/2. Your theta is changing, so it's the change in theta, how the angle is changing. So if I look at this first thing, my first angle would be stopping here. My next angle would be stopping here. And my next angle, if I keep going, would be stopping here. Like I could make how many angles in there? An infinite number of angles, right? Kind of like a Riemann sum idea. So I could put an infinite number of sections into this. And then I add them all up, the sum of them. And this is your r squared. So it's 1/2 theta r squared. It lines up with the same thing back in geometry of your area formula. All right, let's take it up one more notch. How many rectangles, how many sections can I make in this? And you can make an infinite number of sections. The more sections you make, the more accurate your answer, just like Riemann sums were. So it's the limit of 1/2, the sum, I'll bring the 1/2 out, of t equals 1 to n of, that's an n, of f of theta, quantity squared, times the change in theta. Now what does that mean? This is the definition of integration, same idea. Like I said, you can put as many sections as you want in here. The more sections you place, the more accurate your answer is. So here's the formula we're going to use. If f is continuous and non-negative in the interval from alpha to beta, then the area of the region bounded by the graph r equals f of theta between the radial lines of theta being alpha and theta being beta, is, can you say that fast? 1/2. This is the formula we're going to be using. Alpha to beta, these are angles. R squared d theta. And that's what we're going to have. That's the formula we're going to use for all of these. Let me show you how it works. It'd be nice if you could see that last one, right? Okay, here it goes. There you can see it. So number one, The trick with polar graphs is to be careful with what the interval it takes to trace out the polar graph. Watch what happens with this example. Find the area bounded by, they gave you the picture, r equals 5 sine of theta. Well, if this is what r is, let's put our area formula together. Area is, I'm right here looking at this, 1/2 the integral. I don't know the bounds yet. We're going to talk bounds in a minute. R squared. Well, r is 5 sine of theta squared d theta. And it comes down to, and what he's talking about this, the trick, what are the bounds? And so I go and I look at the graph, and I look at this graph. See how the graph is here? That's a 0, 0 type place. That's your origin type place. So I want to know where r of 5 sine of theta, where 5 sine of theta equals 0. This is going to help me find my bounds. 5 sine of theta equals 0. Divide both sides by 5. I get the sine of theta equals 0. I go to my unit circle and I want to know where are the y values. 0, and I know that happens at 0, at pi, at 2 pi, and if I continued on 3 pi, 4 pi, 5, whatever, any value of pi. So I want to know, if this is 0, how far it takes for me to get around to 0 again. Is it pi, or do I need to go a whole value of 2 pi? I know this bottom bound is 0. The question is the top bound pi or 2 pi? So if you go to your calculator and you graph this thing in your polar thing, I've showed you how to do that in class. You change your mode to polar, you put in 5 sine of theta, and you graph it. And if you look at the graph, it turns out that for you to get one full revolution of this circle, you only have to go to pi to get there. They're your bounds. If you go to 2 pi, that's going to be too big. You're going to go around twice, 2 times. So it will be twice as much area as what you want. So it's only between 0 and 2 pi, I'm sorry, 0 and pi, and you're going to check that on your calculator to do this problem. These are typically, AP-wise, these are typically calculator questions anyway. So we're going to do a lot of calculator-heavy stuff in the next couple of sections. So, all right, here's what you do. 0 to pi, you got the values, you put it in your calculator, you're going to calculate out the area. Again, it's a calculator question, and you end up with a value of 19.635. The one thing kids tend to forget to do, they do the integral and they forget to take the half. So make sure that you're ready to go in there and take that half of whatever it is. Every single time. These are all halves. Number 5. Find the area of the shaded region. Well, check this guy out, right? This is the polar curve, r equals 1 minus cosine of 2 theta. This is going to be similar, except there's a bit of an issue with finding what theta is. And it goes back to a lot of pre-calc roots that we've done. So let's see. Set up your formula. A equals 1/2 the integral. We'll worry about bounds in a minute. My r is 1 minus the cosine of 2 theta, that I've got a square, d theta. So again, it all comes down to what are the bounds. So here I am again. It's at 0. I want to know where r equals 0. All right. Swing the one to the other side, it becomes negative. But really, this is negative on this side, so the negative and negatives battle it out and become positive. 1 equals the cosine of 2 theta. Well, you don't have 2 thetas on your unit circle, you only have thetas. So what you want to do is ask yourself, where is theta equal to 1? That's the question. Where does your theta equal, I should say, where does the cosine of theta equal 1? So if you go to your unit circle, you're going to have it at 0, theta equals 0, and the next time it equals 0 is at 2 pi. But you don't want that. You want 2 theta equals 0, and 2 theta equals 2 pi, and you're going to solve that out. Divide by 2. So that means that in our case, we get a theta that is 0. And if I divide by 2 over here, now my theta is pi. So there are my bounds, 0 and pi. So I go to my handy-dandy calculator again and say, pretty please tell me what this would be. 2.3 3, 5, 6 is the goal. How would this change if they asked me to figure out the whole thing, not just this one petal? So we only went once. We went, this is where it's 0. I went all the way around, that's where it's pi, and it closed it up. What do you think it would take to get the rest of this? And I hope you would say between pi and 2 pi. And so if I were to do that, it just doubles this. There's a lot of symmetry involved in these questions. So you can use symmetry. If they wanted the area of the whole thing, just times it by 2 and you're good to go. Okay, there's example 2. Let's go to example 3. Here it is. Find the area of the inner loop of the limicon that's r equals 2 cosine of theta plus 1. They've got some fancy names in some of these things. They're pretty funny. So this one, I could even be saying it wrong. But we were talking in class today, and we think it could be a French thing because of that funny C with the apostrophe underneath of it. But the problem, either way, the problem is treated the same. They want to know how big is the inner loop. What's the area? That would be this piece. All right, so if that's the case, again, here's my 0 thing. I want to know when it gets back to 0. That's going to be helpful in my bounds. But let's set up the area first. My area is, every time, 1/2 the integral of r 2 cosine of theta plus 1 quantity squared d theta. So setting that up is pretty simple, because they're always going to give you that r so you can graph it. All right, so the question then becomes, what are the bounds? Well, the bounds are, again, based upon 0. So I'm going to take 2 cosine of theta plus 1 equals 0. Swing the 1 over, divide by 2. Now I have the cosine of theta is a negative 1/2. Go to your unit circle, figure out where the cosine is a negative 1/2, and you should get 2 pi over 3 and 4 pi over 3. And of course it keeps rotating around. You can get more than that, but you really only need the first 2 pieces of where it starts at 0 and when it comes back to 0. And so that's what's going here. I have 2 pi over 3. I have 4 pi over 3. I go to my calculator, I calculate the area, and I get 0.544 for that one. All right, on to number 4. Find the area of one petal of this rose curve where r is 3 cosine of 3 theta. And so if I look at this one, again, set up your area formula, 1/2 the integral of 3 cosine of 3 theta squared d theta. What are the bounds? Oop. At 0 again. I'm going to show you an example in a minute where they're not at 0. Because it's probably your question. It's always going to be 0. And the answer is nope, not really. Okay, but for now, it equals 0. 0 equals 3 cosine of 3 theta. Divide by 3, you still get 0. Cosine of 3 theta. Then I'm asking myself, well, where does the regular old cosine of theta equal 0? And so I go to thinking about that. I get, first of all, it's going to be, for here, it's theta being pi over 2, right? X is 0. Then it goes to 3 pi over 2. And I could keep going on and on around this thing. So, but if I just want to know what it is for one petal, by the way, because of symmetry, all 3 petals are the same. But I want to know when it's 3 pi. So think about this for, or 3 theta. 3 theta equals pi over 2. Divide by 3, or multiply by 1/3. Maybe you might see it that way. Gives me theta is pi over 6. And then if I take 3 theta equals 3 pi over 2, and I multiply by 1/3 to get divide by 3, same thing. That gives me pi over 2. So I go pi over 6 and pi over 2. They are my 2 values here. This is pi over 6. This is pi over 2. And so I'm going to calculate that out. And I get a value of 2.356. All right, there it is. That's your value for the examples there. Then I took you to, let me see if I can remember which one we did next. I think it was number 7 that we looked at in class together. That was very similar to this, so we kind of expanded on this. I also didn't show you all the detail. There it is. I think you can see it. So let's go to number 6 and then see how this one relates. It's kind of a similar, also with number 4, they could ask you what is it for 2 petals, times it by 2, what it could be for all 3 petals, times it by 3. Like, it's all because of symmetry that you can end up doing that. So I want to take you to number 7 in the practice problems next. They did not give you, they said to write but do not solve an expression that will give the area enclosed by 1 petal of a 3-petaled rose of r equals 4 cosine of 3 theta found in the first and fourth quadrants. First and fourth quadrants. That's going to be kind of interesting to us. Let me find us here. Okay, there we are. So do I know what the picture looks like? Maybe. It's very similar to the one we just did, right? So you go to your handy-dandy calculator, since they didn't give you a picture, and you want to graph what this thing would be. Well, it turns out it looks the same as the other guy did. I'm not the best at drawing these, but let's see. This goes second quadrant. This goes. Now they're all symmetric. I'm not making the best of pictures, but you get the idea. So what is my area? Well, my area is 1/2 the integral going, we don't know what the bounds are, going from, I don't know, 4 cosine of 3 theta quantity squared d theta. Why did I use brackets instead of parentheses? I don't know. Just felt like it. But the question then is, what are the bounds? And so I'm going to take this, just like we did in the last one. Here's my 0, right? They're all connected at 0. So 0, I want to know when 0 equals 4 cosine of 3 theta. You're going to see this is going to turn out very similar to what we just were doing. Divide by 4, I still get 0. Cosine of 3 theta. We just did this a minute ago. And we know that because it's a 3 theta, that my theta values are going to be pi over 6. And this is the same work. I'm not going to repeat it. Pi over 2. We found where cosine was 0. That was originally at pi over 2, 3 pi over 2, but we had to divide by 3, so now I'm at pi over 6 and 3 pi over 6, which is pi over 2. All right, so here's the story. This is in the first and fourth quadrants. So in other words, they want to know what the area of this particular petal is going to be. The one that's in the first and fourth quadrants. And so, pi over 6, is that in the first or fourth quadrant? And you say, yeah, that's cool. All right, so pi over 6 is here. Oh, well, actually it isn't. Well, I'll leave it. It'll come back around in a minute. But pi over 2 is not. Pi over 2 is like up here. That's not going to help me out any. And so this is not, this guy's in the wrong quadrant. Right, pi over 2. That would be in the wrong place. And so I have to figure out if this is my pi over 6, which should be my upper bound, pi over 6, right? I'm thinking of, change my color here. Remember how these angles come off the origin? That would be a perfect pi over 6 deal. But what's this guy coming this way in the fourth quadrant? What would be an equivalent to that? And hopefully you're thinking, well, geez, it should be a negative pi over 6 because of symmetry. And you are correct. This should be a negative pi over 6. That would be still equivalent to 11 pi over 6. I mean, 11 pi, yeah, 11 pi over 6, which is that last little bit in your unit circle, which is the same thing as a negative pi over 6. So here's my bounds. Negative pi over 6 to positive pi over 6 is going to give me, and the whole thing is, they were specific about which petal they were talking about. They were talking about the one specifically in the first and fourth quadrant, which means that your bounds have to be the first and fourth quadrant, which is what you have. All right, so then you go to your handy dandy calculator. Oh, they told you, no, you didn't have to. They just wanted you to set it up. So there it is. There it is. Number 3. Let's go back to number 3. I only wanted to do 7 in that order because it was similar to the one we had just talked about. So number 3 is a limicon of r equals 4 plus 2 cosine of theta. You need to graph it before you can do anything else because you won't know what the bounds are or where it starts or where it finishes. So this one's kind of like an oval egg type of deal, but it comes out here to this point. Now this point, and I only know this because I graphed it on my calculator, is the point 60. This one does not start at the origin like some of the others have. And so it's going to change up my bounds for this, how I find the bounds. But let's go into our area formula first. Do the same thing we've done. 1/2 the integral of 4 plus 2 cosine of theta squared d theta. Now here's what makes this one different. When I go to find my bound, 4 plus 2 cosine of theta, I'm not setting it equal to 0 like I have for so many of these others. I'm actually setting it equal to 6 where it starts. So this is going to be an equals 6. Do you see it's different than the others? So I'm going to subtract 2. Gives me 2 cosine of theta equals 2, or the cosine of theta equals 1. Now you go to your unit circle, you figure out, well, where is the x value 1? And it is at 0 and 2 pi. So it starts at 0, it takes me 2 pi to get back to that again. And so that's what I've got for my bounds, 0 and 2 pi. Again, if you graph this on the graphing calculator, it'll verify that. You want to verify, as he said in the very beginning of the notes, verify your bounds there. So yeah, that's what it's going to be. And so then you go to your calculator and it calculates an area of 56.549. Number 8's the next one that I wanted to do. And I think there's one more after that. Number 8. Write but do not solve an expression that can be used to find the area of the bounded region of the polar curve r equals 3 minus 2 sine of theta. Now you can see this one also is one that doesn't originate at 0, so you're not going to set your bounds equal to 0 like you have in so many of the other problems. Again, why I wanted to picture this one and have you work this one through. Alright, so here's how it goes. I have an area formula. I always start with my area, 1/2 the integral of 3 minus 2 sine of theta quantity squared d theta. So I have to figure out, now remember this is a sine thing, right? So this is the sine guy. So I'm looking at y values for this. So if I look at this, this one has a length of 1. So I want to know where 1 equals 3 minus 2 sine of theta. Let's work our way through that. Take 3 away, you got negative 2. Negative 2 equals negative 2 sine of theta. Divide by negative 2, you get 1. Where does the sine of theta equal 1? And we say at pi over 2. But then on the other side, this guy has a length of 5. Now, it's kind of weird. You might be thinking that you're supposed to use a negative 5, but it is a 5 that equals 3 minus 2 sine of theta. You've got a length of 5 there. So take 3 away, you got 2. Negative 2 sine of theta. And so I want to know where negative 1 is the sine of theta. Where does the sine equal negative 1? Where does your y value equal a negative 1? That's at 3 pi over 2. Now let's look at the picture. Does that make sense? Does it make sense that this is a pi over 2? This is when theta is pi over 2, and this is when theta is 3 pi over 2? And hopefully you're saying, yeah, heck yeah, that looks like my unit circle. And so I've got pi over 2 being this value, and 3 pi over 2 being that value. So it's kind of all fits together. Here we go. Pi over 2 on the bottom bound, 3 pi over 2 on the top bound. And they say set it up, don't solve it, and you're done. So that's that guy. All right, last one's number 11. Number 11, let me find it. Here it is. I even am doing one of the test preps. So, let R be the region in the first quadrant that's bounded by the polar curves of theta over 2 and a theta equaling k, some value of k, where k is a constant between 0 and pi over 2. Well, of course, because it's inside of there. As shown in the figure above, what's the area of R in terms of k? So what they want to know is what's your area. So let's set up our area formula. My area is 1/2 the integral of r squared, theta over 2 squared d theta. And what are the bounds? Well, the bounds are starting at 0, right? Starting at 0 and going to k. All right, so let's play with this a little bit. So that means it is 1/2 the integral 0 to k of theta squared times, I'm looking at this, theta squared, 2 squared is 4, but it's in the bottom, so it's 1/4 d theta. What can you do with the 1/4? Well, hopefully you're saying bring it out. Let them join up with Mr. 1/2. They become 1/8. 1/8 the integral from 0 to k of theta squared d theta. Think integrals. If I integrate that, then I'm going to have 1/8. This is like an x squared. What would the integral of x squared be? It's x cubed over 3, or 1/3 x cubed. Well, if it's a theta, so what? So now it's going to be 1/3 theta cubed going from 0 to k. So what does that look like? Let me pretty it up just a little bit more. 1/3, 1/8 becomes 1/24 theta going from k to 0, theta cubed, going from k to 0. So I've got I'm out of your light, 1/24 k cubed minus 0 cubed, right? F of b, f of a, gives me a k cubed over 24. And that's your answer. What's R in terms of k? Area of R in terms of k. Okay, so that takes us out of section 9.8, and I will see you in class. Shoot me an email if you've got questions, and I'll talk to you soon.